pum. Pum 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 pum. Should I start?
Yes, so Pedro's going to give us his introduction.
Okay, very good. So let me first summarize a couple of things we have seen yesterday and explain something that I promised that today I will explain a little more, that I would explain today a little bit more carefully, that yesterday was a little bit too fast. So, but first a little bit of review, as we said. So we introduced this multi-Reggie limit. It's one particular kinematics for studying two particles going into n particles, which have this hierarchy of energies, such that most processes are suppressed because they involve a huge exchange of energy, right? And so the only way a propagator separating some process on the right to some process on the left, the only way this propagator is not zero is if on the left, say, we have particles 1, 2, 3, 4, 5 up to j, or on the right, of course. On one side, we have all the particles from 1 all the way to j. But then it means that the only three-level graphs that contribute are these combs, are just a straight line given by a sequence of vertices, and where particles furthermore must be ordered like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? Otherwise, all the diagrams vanish. So for example, this one here is 0, because this is not a comb, right? So even if this propagator is good, one of these two is not going to be okay, right? So this diagram, for example, is not going to contribute. Okay, so only those would contribute. But then, if we impose that a given process is 0, that we don't have particle production, right? So let's suppose particle 1 is the leftmost one, and it can attach to a 3 vertex, or a 4 vertex, or a 5 vertex, and so on. If it attaches to a 3 vertex, what is here is an amplitude that we cancelled already. If it attaches to a 4 vertex, what is here is an amplitude that we cancelled already. And it goes all the way until when particle 1 attaches to the big vertices, because then the big vertices, they leave to the right smaller amplitudes that are not 0, like 2, 2, 2, 2, 2, 2, 3-point vertex, or nothing. So those we don't set to 0. So all this we can set to 0, and we get only 4 terms. And therefore, if we impose that this is 0, we get this recursion relation on the vertices of my Lagrangian. Right? Now, furthermore, in this recursion relation here, we have two things. One is, if the theory has Z3 symmetry, Z2 symmetry, C3 is 0, because there's no cubic coupling if you have Z2 symmetry. And if there is a cubic coupling, then the quartic vertex and the cubic vertex, they are not independent, because the seed cancelling the smallest process forced us to set C4 to 3C3 squared. Okay? So we have two options. Either C4 is equal to this value, or C3 is equal to 0. And these two options then lead to two Lagrangians. One without Z2 symmetry, which has a cubic coupling, that's the Bullock-Dugg Lagrangian. And the other which has Z2 symmetry, which is the Sine-Gordon model. So the Sine-Gordon model describes a scalar, phi, right? So this Lagrangian here for Sine-Gordon, what is it? So at least for phi small, it's m square phi square over 2 plus some constant times phi to the 4, right? Which is exactly what we had promised, that there would be a phi to the 4 interaction that would give the leading term when I compute 2 to 2. Right? Now, this Sine-Gordon, you can think of it like a scalar, but it's a periodic scalar. So you can think of it like a belt. You have a belt, and phi is like the angle. And you can twist the angle all the way to 2 pi and hold it at both ends, and then you cannot untwist, right? So if you twist the belt, then you cannot untwist. So it's protected by topology. So this, going from one vacuum to the other, is what's called a kink. It's this topological excitation. You go from phi equals 0 to phi equals 2 pi, and it stays here. Right? This domain wall you cannot untwist. You can also have an anti-kink that you twist in the opposite direction. Of course, now if you twist the bell and then twist back, that's the same as nothing. So now it has the same charge as the fundamental excitations, which are just small ripples, right? Again, you have your belt, and you pinch it, you kick it, and it fluctuates a little bit in the middle, right? So that's the breather. Okay, and the breather, then you have more vibration modes. You have the second breather, the third breather, and so on. It stops at some point. It depends on the coupling of Sine-Gordon. But this is the spectrum of this theory. Okay, and then in the beginning of yesterday's lecture, I told you what was the S matrix of Sine-Gordon. It's this one. We can put the index 1, 1 to indicate that's the scattering of the lightest breather against the lightest breather. 1 with 1. Okay? Now, what about all the other animals in Sine-Gordon? For example, what about the scattering of the second breather with the first breather? Well, that one is also easy, because that one, since the second breather is made out in the sense of bound state, it's made out of two fundamental breathers, I can just multiply the S matrices of the fundamental breathers and obtain in this way the fused S matrix of the bound state. Right? So here is the picture where the scattering of the particle with a bound state, that's the left-hand side, is equal to the scattering with its constituents, which is the right-hand side. Okay? And now you can go on. You can, for example, scatter 2 with 2. You just do the same thing here, you see. So you already have a bound state 2. You scatter with 2 1s, and you scatter 2 against 2. So going in this direction, you fuse more and more and more. Now, you could say that the most fundamental ones, however, would be the kinks and the anti-kinks. Right? I cannot fuse and get a kink, because a kink has a different topological charge. A kink has this charge that goes from 0 to 2 pi. I cannot get it from breathers. Now, what I could do is take a kink and an anti-kink and form a breather. Right? So in a way, the breathers are the most fundamental ones. If I can fuse a kink and an anti-kink, I can get the first breather. Right? So what we would like is actually to have the most fundamental S matrix would be this one here, S hat. So this I did not write last time. So this is now starts to be the new stuff. So what would be this S hat? This would be a matrix. Now it's a matrix where I can scatter a kink against a kink and get a kink and a kink, or a kink against an anti-kink and get these 4 components, which are the easy and hard component. The kink can pass by the anti-kink or reflect. And then, say, kink bar with kink bar could get kink bar with kink bar. And now I have this 4x4 matrix. That's the S matrix. Right? And this, from this S matrix, now I can fuse and obtain, first, I would obtain the S matrix of kink with fundamental breather, and then I would obtain the S matrix of breather with breather, if I knew the kink stuff. Okay? Now you can ask, can I go backwards? Can I unfuse? Can I start with this breather and go backwards? Can we go backwards and guess what is the kink breather? Right? So let's try to do this exercise just for fun to see how far could we go just in this exercise. So what could be the kink breather S matrix? So I want to scatter a kink against a breather. Right? Okay. So what do we expect this object as kink 1? This notation is a bit easier to write down. So what do we expect it to satisfy? So by charge, we expect that if I draw a picture, that this is the kink and this is the breather, I could have the kink here flowing, right? Or maybe let's draw like this. Actually, I must draw like this. Okay. Let me not explain why. Okay. So the kink scatters with the breather, and I could get here a kink flowing. Kink, breather, right? Because we have 1 unit of charge, right? So it would preserve. Okay, and this S matrix by symmetry would also be equal to the S matrix of kink bar with breather. Right? Breather is neutral, going kink or kink bar would be the same. But now we have 2 interesting things. You see that by charge, if I have a kink and a kink bar, let's put some arrows to distinguish, I can form a 1. Right? And here, so that's one type of interaction, and here is another one where a kink and a breather can form a kink. Right? And this tells me that I can form the 1 from a kink and a kink, but that means that my S matrix of kink and 1, if I think of this 1 as being a bound state, I can write an equation of the form, this should be, if I scatter this 1, sorry, 1 second. No, 1 second. Let me go back. Sorry, let me go back. So I want to say the following. So we want to guess this subject, and I want to say that S, king with 1, should obey an equation of S, king with 1 with some argument shifted, times S, 1 with some argument shifted. So where is this equation coming from? It comes from by saying that the king itself can be a bound state of a king and a fundamental particle. Right? The king itself appears as a bound state of the king and the fundamental particle. Right? So that's one relation that we would like to do. To know what exactly we shift by, we will need to know the mass of the kings, but this is one relation we would want. Right. And the other one, okay, the other one is what I was going to write before, and then I was afraid. Okay, this particle 1, so if I want to scatter 1 with 1, I can obtain this 1 by considering king with 1, theta plus tac tac tac, and S king bar with 1, theta minus tac tac tac, where because of king bar and a king bar can give particle 1. Right? And I'm not sure of the shifts, because for that I would need to know the mass of the king and the mass of the breather, but I expect relations like this that start to be constraining. And at this point, I could make an ansatz. So I will say, let me try the following ansatz. S, king with 1, let me try to say that it only has the king flowing, that's the minimal choice. So I will try sinh theta plus some constant b, sinh theta minus b. Exactly like the breathers, they had a bound state whose position was b. So let me try this. Okay? And b is a constant. Right? And now I ask, can I satisfy these functional equations? I know S11, I plug this ansatz here, can I satisfy these functional equations? Okay? And these functional equations, for example, they tell you that it works if B is I cosine of alpha, where alpha is that alpha there. And indeed, that's the correct S matrix for a king against a breather. Okay? That's correct. And we could try, and this would be an idea of the bootstrap. I try to, in a minimal way, try to construct the S matrix of all possible excitations. And we could now try to go backwards to say, unfuse one more time, break down this breather further into kings and anti-kings. Okay? And it's challenging, it's hard to do. You could imagine trying to do this exercise. The next step is going to be harder, because we know the explicit expression for this S matrix. I did not write the elements, but it's not something as nice as this. So this is just like a simple function of sinh theta, this one as well. This one is an infinite product of gamma functions. Okay, so it increases in complexity a little bit. But from the point of view of these functional equations, conceptually it's what I said. Okay, so why are these guys much more complicated? Because with a king and a king bar, it has the quantum number to have all the breathers there. So it needs to be more complicated. You cannot just it needs to do more things than these breathers are required to do. But this is how we would try to bootstrap, and this process of trying to get a full set of closed equations is what is called the integrable bootstrap. Okay? So this is one type of bootstrap. So what do we know about that S matrix? If we were to do this, we would find something remarkable for this S matrix of king and anti-king, that it's a real S matrix, and we would find that if I take this S matrix for the king and anti-king, suppose I could find it by undoing this fusion all the way, I would find that this S matrix, if I multiply it in two different orders, I get the same result, and that's a property of integrable theories. That means that the scattering factorizes, and it doesn't matter when I scatter because I can freely shift wave packets in integrable theories. And I wrote yesterday, and then I said that today I would say a few more words to be a little bit more careful. I said statement. The claim was the S matrix has a total momentum conservation, and then one particular choice of I0 times this product of S matrices, and another choice of I0 times another order of S matrix. So let me just show you why this is a very nice form for an S matrix. Because suppose I convolute this S matrix with these three wave packets. So I take this S matrix and I convolute it with these three wave packets. So what am I doing here? I'm saying that P1, P2, and P3, they are wave packets. This tau, let this tau be large, with momenta K1, K2, and K3. Right? So I'm putting some wave packets with momenta centered around K1, K2, and K3. Right? What I'm also doing here is I'm shifting the middle guy. I'm putting I beta P2 that shifts particle 2. So what does it mean? If beta is equal to 0, I'm preparing the three wave packets that will meet at the same position at t equal to 0. But if beta is very large, I'm shifting the middle wave packet to the right or to the left. Do you agree? So what should this be doing? What do I want from a physical theory? I want that if I shift my wave packet way to one direction or to another direction, what I want to happen is the process to be localized on this process or this one for beta going to say plus infinity or minus infinity. Right? Because if I prepare wave packets that are going to meet here and then there 100 kilometers and then there 200 kilometers to another direction, I want the processes to be factorized. Right? So let's see that this works nicely. So this beta is very large. And I integrate over P2. So what do I want to do? I want to move the contour a bit up or a bit down, depending on the sign of beta, to make it exponentially small. Right? So I am integrating at real P2. Remember, this P2 has an arrow, but it's 2 dimensional. This is a number. So I integrate over this number P2. And what I can do is I move the contour a little bit up or a little bit down. What happens for this regular term? Nothing. So it just means that I move up, I move down, and this regular term is exponentially small, doesn't contribute. So that's what I expect. If I have a theory which is gapped, it has some interaction range. So if I prepare my wave packets to scatter in a very separated range, it doesn't contribute. So this never contributes. Doesn't matter if beta is positive or negative. What about these ones? Well, these ones depends. So if I need to move P2 up, I need to first pick the pole at P2 equal to P5, right? So when I move it up, I pick P2 equal to P5. So let's suppose this is minus plus infinity. So when it goes to plus infinity, indeed, what happens is that I want to move up, say, but as I move up, I pick P2 equal to P5, and I'm localized on this. So I pick this pole, and after I pick the pole, I continue moving up. So after I pick the pole, the rest is 0. But I do need the contribution of the pole. So what do I get? This term. And if I go in the other direction, I want to move down. So this one I don't care. And immediately I pick this pole. Right? Because it has a different I0. Right? And therefore I pick it. I localize on this term plus exponentially small. Right? So these two terms with relative minus, and there is a beautiful minus sign here, right? Because in one way I close like this. In the other way I close down. I close in the opposite direction. Right? And 1 over 2 pi I and so on, because the residue is 2 pi I. Right? So it beautifully works and it gives exactly what we expect. Okay? So this was the careful explanation. Okay. So let's make one more trivial comment about sine Gordon, since we are doing sine Gordon in this blackboard. Yeah, we can make it here. That this sine Gordon S matrix, right? You remember that this S matrix was equal to 1 plus I t of theta over sinh theta, where t of theta is what we compute in perturbation theory, right? And indeed, this S matrix S is what? Is, if I subtract, I write minus, plus, and then I expand, I don't know, it's something like 1 plus 2I sum of sine alpha over sinh theta to the n, right? From n equal to 1 all the way to infinity, right? So a very trivial comment is that when n equal to 1 is the 3-level result, right, which is just gives t equal to a constant. And when n equal to 2, 3, 4, these are loops, right? Now they have to do Feynman loops. So when n equal to 2, it would come from loop diagrams where I have the 4-point vertex, 4-point vertex, etc. Right? So I would have to start doing loops. It's kind of amusing that such trivial expansion that we cannot find some simple argument with all this technology that we have for perturbation theory of scattering amplitudes, that there is no simple way of just looking at these diagrams and these loops and immediately showing that this is true, right? But to my knowledge, it's not known. Yeah, people did 1 loop, they did 2 loops, suffering a lot, but this is the result. You see, it's just sine alpha to the n. I mean, it is just a power of the 3-level result, roughly. Of course, roughly, because alpha is not exactly the coupling. You would have to find the map between alpha and the coupling. So it reshuffles a little bit. But still, it's basically as simple as it could be. So let me now say a few words about the S-matrix for Balog-Dug theory. So what is this S-matrix for Balog-Dug? Now, this S-matrix for Balog-Dug, I will tell you what it is, but let me try to argue so that you see that there's not that many things that you could write. So one thing that we want for Balog-Dug is that there exists a cubic coupling. So there exists, if you want, a bound state whose mass is equal to m to the mass of the external guy. So the bound state is the particle itself. There is a cubic coupling. Okay? So it's a bit different from Sine-Gordon, where you had a coupling that you would tune, and when the coupling goes to 0, the bound state becomes weakly coupled. And when the coupling is large, the bound state could become heavier, lighter. Right? So one thing we could try is to just take, let's denote this type of factors here. Let me call this factor here, we called it in the lecture F alpha. It's called a CDD factor with parameter alpha. So we could try F with parameter 2 pi over 3, right, of theta. And this 2 pi over 3 is such because when theta equal to 2 pi I over 3, this corresponds to S equal to 1, or actually, okay, let me 2 pi I over 3. I can put like this, pi over 3. Yeah, let me put 2. Okay, let me just make a comment. F alpha is equal to F pi minus alpha. So I can put whatever I want, but for the argument, let me explain pi over 2. So when I put an F alpha, there is a pole at 2 pi I over 2 and 2 pi I over 3 and pi over 3, and at theta equal pi I over 3, S is equal to 1. That's the value of the cubic coupling. Okay, you can check using the relation between S and theta. Okay, you can also remember that it was correct. 2 pi I over 3, right? Remember that in these pictures, theta was this angle, right? So in a cubic coupling, the angle is the same, so it's 2 pi divided by 3, okay? When the coupling is cubic. Okay, so this would be a first starting point. I'm putting a pole at the right position, right? But this has no coupling here. This has 2 problems. One, there is no limit where this becomes identity. This is just some S matrix, right? So it doesn't have any coupling that it's becoming the identity, right? The second problem, if you remember, is that this guy has the wrong residue at S equal to 1. If you remember, we said that S channel and T channel, they must have opposite signs. And this guy would have the right channel, the right sign for being a bound state of mass square root of 3 and not 1. Okay? So the T channel and S channel are in the wrong position. So you could say, okay, but then I'll put just a minus sign. Okay? I flip the sign of the T channel and S channel. But if you do it, then you screw up fusion, because you expect that this S matrix needs to obey that S of theta should be equal to S of theta plus I pi over 3 times S of theta minus I pi over 3. That's what we can call the cubic condition. It's the condition that the particle is its own bound state. Okay, so this would have 2 problems, that either it has the wrong signs for the residues, or if I try to fix it, then it doesn't fuse. Okay? And furthermore, it doesn't have a good weak coupling limit. It has a pole. So let's make it have a good weak coupling limit by putting a 0 nearby, because a pole with a 0 is close to 1. So let's put a 0. Let's multiply this by a function f of, say, minus 2 plus b times pi over 3, where we will think that weak coupling will be b to 0. So then if I multiply these two factors, I have f alpha times f minus alpha, and you see from the definition this will be 1. Right? And if b is small, you see that because of this minus sign, it's putting a 0 close to that pole. Okay? So this would have the property that this function, for b close to 0, it is indeed equal to 1 plus a small pole, a pole with a small residue. Do you agree? Now this, if you plug it in this relation, now it doesn't work. So you need a minimal modification, and the claim is that the minimal modification is to multiply this by f of minus b pi over 2b pi over 3. Okay, let me check the 2's. Okay, and this factor is an extra 0 that you need to put. This is so that fusion, it's required by fusion. And then fusion is working, everything is working, and it has a good weak coupling limit. You see, when b goes to 0, this goes to 1, this product goes to 1, and this would have a good limit. So this would be the simplest possible solution with a cubic coupling and a good fusion, and this is the S matrix of Balogh-Dugg, if I fix the factors of 2. And the factors of 2 are almost okay. So b minus 1 with a 2 outside, or then I should remove the 2 from there. Okay. This is indeed the S matrix of Balogh-Dugg, and as I said, we bootstrapped it now by trying to guess what would be the simplest condition that would obey fusion and have a cubic coupling. Right? Now let's take this S matrix and expand it at b going to 0. Right? And this S matrix, if you expand this S matrix, S of theta, and you expand, what do you get? You get 1 plus I over sinh theta. And now I'm right, whatever I will write here is t, right? Is what we compute from Feynman diagrams. And I will write t by converting from theta to s, such that we recognize a little bit more what we get in perturbation theory where we use s. And what we get here is the following. We get pi beta over s minus 1 plus pi b over 4 minus s minus 1 plus, and now there is a constant that I'm going to write in this funny way. Okay, where b is small. Okay, so what do we recognize here in this S matrix? What is this process here? This is an S-channel pole, right? So this guy is representing an S-channel pole, right? So what is the residue? The residue here of this pole should be g square, which should be C3 square in our notation, that the vertex was C3, and apparently the identification is that this is pi b, right? What about here? What is this? What is this? What is 4 minus s? M equal to 1. What is 4 minus s? Remember? So we had s, and 4 minus s was t, right? This is the t channel, right? So this would be this diagram, right? Where t is 4 minus s. Nice, okay? 4 minus s, minus 1. It's the particle being exchanged, the same residue. It's okay. What is this? The U channel, right? If I write the propagator of the U channel, right? It's right? Because u equal to 0, we have no momentum transfer, and so the U channel will contribute to this constant. right? And therefore what remains is a constant which is given by a contact interaction. So this is C4, right? That we see C4 is 3 times pi b. And so what is C4 is 3 times C3 squared. Right? It's 3 times what we get here. Right? And that was exactly the condition that we had before once we had imposed that there was no particle production. Right? So what are we seeing here explicitly, experimentally? We are seeing that we are finding, from this bootstrap point of view, we find the relation between C4 and C3. And where is this relation between C4 and C3 coming from? Well, it was forced upon us by requiring this fusion relation. Right? So we saw that fusion for us, this condition here, from this bootstrap point of view, came as a consequence of requiring this fusion. Whereas before, that condition here, there, came from T2 to 3 being equal to 0. Right? From the absence of 3 particle production. Okay? Now that's the same thing. Let's explain why. Let's explain why this condition is the quantum version of what we did yesterday. Because what would happen at the quantum level for the process 2 to 3? Suppose I have a process where 2 particles goes to 3 particles. Right? Now this process, 2 particles goes to 3 particles, should have singularities when there are on-shell processes that I can draw. And here are 2 on-shell processes I can draw. This guy here could become on-shell in the following situation, when I have a particle that is formed that becomes on-shell, that then scatters with the other 2. This is an on-shell diagram. Another on-shell diagram I can draw is the one where I take this wave packet and move it down, and then it scatters here. These are 2 on-shell diagrams I could draw. Like before, when we had this Young-Baxter that we had to move the line, and because one diagram is obtained in one direction and the other is obtained in the other direction, if you remember, there was a minus sign between the 2 from shifting this. Similarly, here, there would be a minus sign between these 2 diagrams for the same reason of shifting this wave packet. Right? And we want to say that at the quantum level, this guy is 0. So if it is 0, it means that this singularity that is inside this diagram must be equal to 0. So we can interpret that fusion relation as a necessary condition for setting 2 to 3 equals 0. 2 to 3 is equal to 0. It requires that we have this fusion relation. And so it's not so different from before, because before it was exactly what we did at 3 level. Okay? So we see that this is equivalent to the quantum version of what we did yesterday. It's necessary for 2 to 3 being 0 at the quantum level. And so we can say that this fixing this bootstrap S matrix was a version of that. Let me make one more comment, which is that this S matrix obeys fusion for any value of b. Right? This is just a functional relation, so you can plug it there and obtain this for any value of b. And here, if you want this guy and this guy to be zeros, we set b close to 0. Right? In particular, when b is negative, then this guy starts becoming a pole. Right? And if b is right, so yes. So you could ask whether there are other solutions with 3 factors that also obey the right fusion relations. So let me write another example of an S matrix which has 3 such factors, and that obeys this right fusion relation. And this is this one, S, and let me put H as an index, which is equal to S to F. I'm going to write an S matrix of 2 pi over 3, F of 2 pi over 5, and F of pi over 15. these two values, once I fix this one is fixed because I need fusion to work. So it's the same as once I fix this guy here, then this one was forced upon me. And this S matrix is the S matrix that Zomologikov found that you get if you take the criticalizing model in 2 dimensions and perturb just by magnetic field. And then this would be the S matrix of the lightest particle of that model. So this H would stand for the magnetic field if you perturb the criticalizing model by magnetic field. So it's a special S matrix. It has a special spectrum that you can go on and read off from these masses here. And we will encounter this model again by the end of the lecture today or maybe the beginning of tomorrow's lecture. Okay? But that's just another theory for us to know. As I said, it's called Zomologikov's E8 theory. And it's obtained by taking the criticalizing model, right? That's just free massless fermion. And then, if you might know that if you deform by changing the critical temperature, you go to a free massive fermion. That's the easiest deformation. If instead you deform by just magnetic field, you go to this called Zomologikov E8 theory, which is also an integrable theory. If you deform by temperature and magnetic field, you go to a non-trivial theory, which is not integrable, that people don't know how to study analytically because it's not integrable, and people study it numerically. So it is my understanding from the notes that she already mentioned a few things about this. I think she said a few words about this, but maybe not much more than this, right? So here is this theory showing up again in this school. Okay. So now I would like to switch gears a little bit and do some complex analysis. Would it make sense to make a break of 5 minutes to let I erase all the blackboards and so on, or will it create total chaos? Okay. Because now we'll really switch gears. So now we'll stop a little bit, everything we are doing. We are going to now go into the bootstrap. The idea of bootstrap is you explore analyticity and you take water out of stone. And that basically requires using some cool things about complex analysis. And so what we are going to stop now is make a break and do some, I will recap a few things that you probably know about complex analysis, but which will then have a direct translation for S matrices, which are functions of complex variables. Okay. So we are now in pre-bootstrap mode, doing some complex analysis review. Okay. Since it's really a change of topics, is there any question about what we have just finished now? So we finished with examples and with a general survey of examples, and now we go to bootstrap. So it's a good time to ask about examples. Yeah.
Is this an okay diagram for the, like, in the combs that you draw, you only have like 1 or 2 things coming up, but you could have lots of stuff?
Yeah. So the question was whether we could have diagrams like this, cubic, and then many, and then quart. It could be, yeah. This is good as well. What matters is that it's ordered. Yeah.
So, S matrices seems to satisfy certain algebraic structures such as fusion rules and the Serre relations.
And what? What's the second one?
Serre relation, the one where you are moving.
Okay. That's called Serre relations. I see. Okay.
So generically, are the integrable models have S matrices which are like representations of certain algebras?
Yeah, there's lots of mathematics behind all these S matrices and quantum groups and Yangians and yeah. There is a ton of mathematics for those that like mathematics. Yeah. But it's not really all this quantum algebra language and so on. It exists, and there are nice reviews on it by Fadev, by Kevin Costello, by many people, but it's not really the language that I'm very familiar with. Okay, so good. Okay, so we'll do complex analysis, and I would like to recall a couple of simple things about complex analysis. The first thing is something called the maximum modulus principle. And the maximum modulus principle states that suppose I have a region, and there is a region R, and there is a boundary of that region R. And at the boundary, I have that my function is bounded. So I have some function f of z that is smaller or equal than 1 at the boundary of a region. And suppose the function f has no singularities inside that region. It's a molomorphic function without any singularities inside, no poles. then the maximum absolute value principle is just a statement that if this is true at the boundary of R, this is also true in the full region R. Okay? And that's equivalent to saying that functions don't have maxima. Functions don't have local maxima. Okay? And that's obvious, right? Because a function is just the average of all the points around it, right? By Cauchy theorem, if you do some contour integral, you see that the function is equal to the average of the points around it, so it cannot have a local maximum value in absolute value. Do you agree? You can also say that close to any point, what is my function? Is some constant plus z minus z0 if it's regular to some power, whatever that power is. Right? And just by analyzing the vicinity of this point of a function like this, you can see that there are directions where the absolute value increases always. Right? So this is always true. Okay? With a 1 here, otherwise it's not very meaningful. Okay. So what in particular, if you ask what's the maximum value that the function can have here, the maximum value that the function can have here is equal to 1, and what function saturates this bound is the function f of z equal to 1, right, the constant function. Now functions, the kind of functions that we are dealing with, for example, in these S matrices, they have poles, right? Like poles at the bound state. We are not dealing with functions that have no singularities. They have some poles. So here is a better toy model for something that we might want to do. Suppose I have a region, let's say it's a unit disk. Okay? So this is the unit disk. Absolute value of z equal to 1. And now I have a function that has a pole. So my function f at the origin is g squared over z. That could be already a better toy model for our S matrices, that there would be a pole. And at the boundary of this disk, I say that here f is still bounded, exactly like in our S matrices, where we have unitarity at the boundary, which are the cuts in our case. So if we map the complex plane to the unit disk, we would land in a situation like this, right? So in fact, this example could be already exactly relevant to what we are saying, because we could map the complex plane minus a cut to the unit disk, then it would be exactly this problem we would have to solve. So we could ask here, what's the maximum value of G? How big is the coupling? And this would answer a question in quantum field theory. How big can the residue of an S matrix be? So what's the answer here? Well, we can say, let me construct a function h of z, which is my function f of z divided by 1 over z. Now notice that this function, because we divide by a pole, has no poles inside the unit disk. But notice also that 1 over z, when the absolute value of z is 1, 1 over z has absolute value 1. So this function h is the absolute value of this function h is smaller or equal to 1 on the boundary of the unit disk, right? Because on the boundary, this is absolute value 1 and this one has absolute value smaller than 1. So h is smaller than 1 at the boundary and has no singularities. So h obeys the conditions that we set, right? So h of 0 in particular is smaller than 1, everywhere is smaller than 1. But what is h of 0? H of 0 is just a residue of f. And that's g squared. Okay? So we are done. The maximum residue is 1. That's the answer to this problem. Okay? So what's the maximum? The answer is equal to 1. What function saturates it? The function optimal is the function 1 over z. Okay. Let me make a small comment. I can't just do mathematics. Yeah, I have to say a few words about S matrix. Why is this directly related to S matrix? Because in S matrix we have 2 poles, and here we have 1 pole, right? Well, but that's not a big issue, because remember that we have these cuts, and we have a pole here and the crossed pole here, and then there is crossing symmetry, right? And because there is crossing symmetry, it's enough to consider the right of the plane. It's enough to consider this region here. If I know this region, I know everything on the other side. It is just given by crossing, right? And in particular, this line is identified with this line. Right? So I can map the left part. I can find a map that maps this to the inside of the unit disk, right? Where this identification, this cut, would become this point, then this would be infinity, and these lines that are identified would be some segment here, where this is identified with this. Okay? Right? This line here. You see? So, no, actually not here. Sorry, it touches infinity here. Okay, so this would be this dashed line. Okay, so I could just map the left part, the right part of the upper plane to this region. Then I find the maximum coupling. Automatically it translates up to a Jacobian to what's the maximum coupling here. Right? So automatically I learn about what's the maximum coupling here, right? Because this cut here, this part here, is just this cut here, right? So the function is bounded here by unitarity, so it's bounded on the disk. Right? So automatically we get. But another thing we could do is map the full plane, right? Another thing we can do is map the full complex plane to the unit disk. If we don't want to be careful about crossing symmetry and identifying things, the simplest thing to do, let's also work it out how we would do it, would be to map. By the way, this exercise, finding these maps and so on, are in the notes. Would be to take the complex plane and map the complex plane to the unit disk. That is, this kind of foliations. Would be mapped to the disk, where I would have just some foliations like this. Right? And if I do this exercise, then the poles that I get here now become two poles here in the unit disk. Right? So here now, let's see what the problem becomes. And then this A, B, C, D become A, B, C, D. You know, A talks to C. Okay? And now what we would have here? We would have a function that has a pole, g square over z minus z star, and another pole, g square over minus z star, and it's an even function that's crossing symmetry, and we want to ask what's the maximum value of the coupling for this function. Right? What's the maximum value for this possible coupling? Okay? Is it good? So let's solve this problem. So how do we do it? We just say, now I have to divide by the poles again, f of z. Let's divide by a function that has poles at this position, to remove the poles to be able to use the previous theorem. So let's do it. Let's divide by a function that has poles. So we put z square minus z star square. Okay, now we have a problem that z square minus z star square is not a phase when z is 1. And I want it to be a phase, right? Here it was crucial that at the boundary this was a phase. So at the boundary, the conjugate of z is 1 over z. So I want to put upstairs what? 1 minus z square z star square. This is just a complex, now it's a phase, because z is 1 over z at the complex conjugate at the boundary. Right? I could write here with 1 over z square, but 1 over z square is itself a phase. I can multiply everything by z square not to put a singularity. Okay? So this is the correct thing to do. I'm dividing now by a phase. This is a phase. And notice that this, I'm not introducing zeros or anything because z is inside the unit disk. This is inside the unit disk, so this is never 0. Right? So I'm not dividing by any 0. And this here is absolute value equal to 1 at the boundary. But then this function h of z is smaller or equal than 1 everywhere. Right? And therefore, the optimal value, h of z star, right? H of z star, at z star, I get basically g squared, and g squared is smaller or equal than 1, up to some Jacobians maybe that I need to compute. Right? So what do I learn? I learned that the maximum value of the coupling, I computed it. Right? I can compute it as a function of z star. And what is z star? Z star is the mass of my particles. It's my positions. So in this way, we find what's the maximum value of the coupling for a theory that has a single bound state. Right? So that's the problem we solved. We solved the following problem of asking, suppose I have a quantum field theory, and there is a bound state, M bound state, and we just computed what's the maximum coupling G that this S matrix could have. And if you plot it, you find a shape like this. Right? Because we computed that as a function of Z star. Carrying out all the Jacobians, this is what you get. And what is the S matrix that has the optimal coupling? Well, the optimal coupling, as we said, is when this ratio is exactly 1. Right? In other words, this is the optimal S matrix. Right? This function is the function with the optimal S matrix. And now you can ask, how does it look like in terms of S? I mapped from the complex plane S to the unit disk Z, and I see that in the unit disk this is the optimal S matrix, the one with the biggest possible coupling. Let me undo and go back to S. How does this S matrix look like? Okay? And the S matrix you get is the Sine-Gordon S matrix that we have been discussing. So the breather S matrix of Sine-Gordon is the quantum field theory with the biggest possible coupling. There is no theory where the coupling between the lightest particle has a bound state with a bigger coupling. So this is the mathematical solution. So we see that this bound on the space of theories, this here is allowed, here is excluded, and here at the boundary lies Sine-Gordon. So the bound is optimal, at least on this side. I cannot change it because there is a theory at the boundary. Right? So I cannot lower the bound further because I want this theory. This S matrix here is the S matrix of Sine-Gordon that we computed for the breathers. So just to summarize, so mathematically we have this maximum absolute value principle that says if functions are bounded at the boundary, they are bounded inside the regions where they take values. If functions have poles, you just have to be a bit more careful about taking care of the poles. But again, same story. If the function is bounded at the boundary, you bound the strength of the singularities inside. Right? And physically, what's happening? We are saying that if I have a quantum field theory, and it has a coupling that measures the interaction between my particles, there is a maximum that it can be. And what's the physical intuition, or one physical intuition? Suppose it was bigger. What would go wrong? What would happen if I would continue increasing the coupling? But then I have, say, my breathers that exchange this breather and they create some interaction force. And if I were to increase the breather, it would be incompatible with having only one bound state. I would start forming more bound states. It's like I start getting chemistry. I start forming more molecules. Or the coupling is bigger and the binding energy decreases. So intuitively, there should indeed be a maximum coupling beyond which I start forming more bound states and getting a contradiction in my spectrum. And indeed, that's what we find mathematically. We just impose that the function is bounded and we get this pulse. Okay, so it was not exactly just complex analysis. So, but this is basically what I wanted to say about maximum absolute value principle. Yeah. Yes. Let me just make one comment, one trivial comment. As I said, this is another way of solving the problem. this, if I find a map that maps this to this, right? Just the right part, I map it to the unit disk. Then the maximum coupling is 1, and then I have to translate with a Jacobian, the same story, right? And the optimal function is the function 1 over z, right? But I said that the optimal function is sine Gordon. It's that S matrix there. So that sine Gordon, the CDD factor also has an interpretation. It's the map from the right half plane to the unit disk. You can check that that S matrix does that. So 1 over z is nothing but the inverse of the sine. 1 over z is the sine Gordon S matrix. Okay? So sine Gordon does that. It's a map. Yeah. Okay. I will come back to this to this maximum value of couplings tomorrow. How much time do I have today? 20 minutes. Okay. Okay. So today I want to finish some small comments about some complex analysis things. Okay. The next thing I was going to do is tell a little bit about dispersion relations. What's a dispersion relation and how? But I think you probably, yeah, we don't need it. Let's skip it. So let me tell about something. Or let me just do a little bit, do one thing which I think is interesting. So, because it's some words that you might have heard and it looks like something fancy, and it's not something fancy. So suppose I have a function that has a cut, and so this function, there is a discontinuity of my function here, right? So the function, if I go slightly above and I go slightly above, there is a g of x plus I0 minus g of x minus I0 is some row of x, some discontinuity. Right? If I go through two different paths that encircle this. And suppose there is a pole, so my function also behaves as g square over z, and this is this cut starts at some z star bigger than 0, say. And then I have z. And suppose that here at infinity, my S matrix decays as behaves as say 1 plus some constant over log z. So it approaches 1, but not so fast. It goes to 1 as 1 over log z. Now this is actually something that could happen. Suppose we are in the context of S matrix, then remember that we said that on the cut we have unitarity, the S matrix is bounded, right? There is also a left cut that I'm ignoring. We can easily see how the equations are going to change if we have two cuts instead of one. So it's bounded at infinity. So indeed going to 1 at infinity is natural because the function is bounded by 1. So as I go to infinity it should go to 1. Okay? But it could decay slowly. It could decay like 1 over log s. Right? So this is typically, for example, what you will get if you have some asymptotically free theory. You will get these typical logs. So indeed the ON sigma model that Juan spoke, for example, the S matrix decays as 1 over log s. It approaches 1, it approaches the free theory slowly, 1 over log s. The sine Gordon theory, no, it's 1 over s, for example. The one we wrote now, it decays faster, like 1 over s. And then we ask, how do I write a relation that gives me my function if I know this discontinuity? Okay? So let me just tell you, what's the naive idea? The naive idea is to say that, let me write s of z minus 1, right? And I say that s of z minus 1 is, let me write like this, the contour integral dw over 2 pi I around the contour where W is around Z. So I start with my point Z and I do a contour integral in the W plane. And I just write S of W minus 1 divided by Z minus W. Right? So this is a true statement, right? I just do a contour integral around Z equal W and I pick the function. So Z could be a point here, and I'm starting with a contour integral here. Right? Now what would be the problem with this? The problem with this would be that now the next step is to blow this contour. Right? And as I blow this contour, right, then I blow the contour and I pick the pole and the discontinuity by opening up the contour. Right? But the problem is just that it will not decay fast enough at infinity because there is a log here. Right? So that's a bit annoying. But that's not a problem. You just say that you explicitly divide here by some z minus whatever value, some z naught, doesn't matter which one. You just pick any reference value. Now this function decays as 1 over z log z, so that this function now is good. So all you have to do is put here w minus z naught. Right? And now when you open up the contour, what do you conclude? You conclude that s of z minus 1 equal to this, you multiply to the other side, z minus z naught. Right? And then as we blow up the contour, there is this pole at there is the value at w equals z naught that just gives some constant. Right? I plug the pole, I get z minus z naught here, and then s of z naught minus 1, that's a constant. I can pick the pole at z equal to w, at w equal to z, sorry, that gives me what I want. Okay, that's already, no, that's where I start. So I blow up, I don't pick that one. Then I pick the one at z equal to the pole, so that gives me at the pole g square, at the pole I put z equals 0, I get g square over z times minus z0. Okay, such that you see that when you put z equals 0, you do have the behavior g square over z. Right? Plus the integral starting from z star and going all the way to infinity, dw rho of w divided by 2 pi I z minus w minus z0. Okay. So you have probably seen these dispersions without this term, where I just do the trick without the z minus z0. It's the most common thing. And this, doing this trick with one such factor to make it convergent, is what's called one subtraction. So this is dispersion with one subtraction. So this thing here is called one subtraction. So it's something that people that do dispersion relations use a lot. We see that here, because the S matrix is bounded at infinity, it is bounded at infinity. One subtraction is enough for sure. For example, it works with this 1 over log z, but it always works, right? Now the integrand decays as 1 over z square, so it's okay. And in higher dimensions, you might need 2 subtractions for dispersions to always converge. So you can show that the growth of amplitudes is such that in higher dimensions, you might need 2 subtractions. But this, you see, is a way that if you know the discontinuity of the amplitude, if you know the discontinuity of the function, you get a representation for the function in terms of its discontinuity. And that's something very useful in S matrix theory. It's a way of parametrizing S matrices. You can just parameterize their discontinuities. And if you have more cuts and more poles, when you blow the contour, you get extra integrals along those cuts and poles. Okay. So, right. So this is all well known. And what I'm going to tell you now, at least I did not know until a a few months ago, which is a generalization of this maximum absolute value principle. It's a trivial consequence of it, but which, to me, it looks a little bit like dark magic, that you can extract things out of it. So, and let me tell you a little bit what this is. So this is what's called the Schwarzspec lemmas. So okay, Reggie was hard, imagine Schwartz. Okay, Pick is okay. Schwarzspec theorems. Or lemmas, yeah. S-C-A-R, yeah, it's okay, be nice. Okay. So the Schwarzspec theorem is a way of, given some function f of z that is smaller or equal than 1, construct a family of other functions, let's say f, j, that are smaller or equal than 1. And if we could get some mileage out of f, then we can get more mileage out of this f1, f2, f3, out of this family of functions. Right? We saw that already. From 1 we could get some information. From more than 1 we could get more information. Okay. So the basic idea is very simple. Let me exemplify it by considering our region to be the upper half plane. So let's suppose we have the upper half plane. We have a function f that is smaller or equal than 1 in the upper half plane, and there's no singularities in the upper half plane. Okay. So we can say, in fancy words, okay, maybe not so fancy for the level of the audience, but we can say that this is a function from upper half plane to the unit disk, right? Because it's smaller or equal than 1, it's saying that it's a function to the unit disk. Okay? And now we can construct the following function. Let's construct the function f1 of z. It's a function of z which has a parameter which is w. And w belongs to the upper half plane, okay, which I called h, belongs to the upper half plane, but it's a parameter. The function is function of z. And this function is the following. Is the function f of z minus f of w divided by 1 minus f of z f bar of w. Okay, so you see that it's not an holomorphic function of w, right? It's the bar of it has f of w and the conjugate of f of w. Okay, but it's an holomorphic function of z. F of z appears here and here. Okay, and it's this divided by z minus w over z minus w bar. Okay, and that's the definition of my function f1. And you can easily check that this f1 has no singularities, no new singularities. Why? Because you see z minus w bar is in the lower half plane, so this is never 0. And z minus w is indeed a singularity. It's a 0 when z is equal to w, but when z equal to w, this cancels. So this has no new singularity, so this still has no singularities. And what about the boundary of the disk? At the boundary of the disk, z is real, so I have real minus w is real minus w bar. This has absolute value 1. And this is what's called a Mobius transformation, which is a transformation from disk to disk. If f is in disk, f bar is a parameter inside disk, this is a Mobius transformation, it's from disk to disk. So this full function is also of the form upper half plane to disk. And this function f1 is indeed smaller or equal than 1 everywhere. Okay.
Sorry, Pedro, did you say
Yeah.
disk to disk, but you wrote D to B?
Yeah, this is yeah, just one disk. Okay. And so we start with a function f, and we construct a function f1 that now for any parameter w, I get a new function that I can impose that it's smaller or equal than 1 everywhere. Right? And now I can go on, because this was given any function f. So now I can construct f2, which is equal to the same as f1, where I use, instead of f, I use f1. Right? I plug f1 here. Right? And then I construct f3, f4, f5 recursively. So I can go on and I construct a sequence of functions f1, f2, f3. So f2, for example, let me just emphasize, f2 is a function of z and of two complex parameters, w1 and w2. The one I use to construct f1 and then the one I use to construct f2. Okay? So let me illustrate in the remaining 5 minutes, let's apply this Schwarzspec theorem for some S matrix application. And the S matrices that this will be particularly, actually no, sorry, I changed my mind. Okay. Yeah. Let me say one thing. Suppose I have a theory of massless particles. Okay, which is some effective field theory which is weakly coupled, where my S matrix is 1 plus I times the energy S with some parameter alpha plus beta times S square plus dot dot dot. Where I have a low energy expansion, I'm expanding at low energy. In other words, to leading order, it is e to the I alpha S, right, to leading order. Which, you see that to leading order, alpha better be real, otherwise this violates unitarity, right? So alpha better be real, or have some imaginary part which has the right sign, otherwise we immediately get something bigger than 1. Right? So what do we see here? We see that alpha needs to be real. And remember, what is alpha? How do I compute alpha if I have some Lagrangian? Alpha times S. How would it come about? It would come from some quartic interaction, right? With some derivatives. I would have some derivatives. The derivatives I'm drawing by this arrow. And I have some force field term with some derivatives and coefficient alpha in my Lagrangian. Right? And we see that when we get an effective field theory with some quartic interaction with two derivatives, it will generate S times alpha. And then it will generate this S matrix. And for any value of alpha, this is a phase. Right? But now, what happens? What happens is now that if I say that this is the correct S matrix, when the particles are massless, what happens is that these cuts, the S and T channel poles, collide. Because the cuts, if you remember, this one starts at 0, this one starts at 4m squared. So when particles become massless, these cuts collide. Okay? So for massless particles, we should restrict to the upper half plane. We should define the function in the upper half plane. So for massless particles, this function is giving me the S matrix after these cuts collided. So the cuts collide and I am here in the upper half plane, and here in this cut S needs to be smaller or equal than 1. Right? But then by the maximum absolute value principle, we know that S needs to be smaller or equal than 1 everywhere. Right? So it needs to be bigger than 1 when I go not in the physical region of increasing the energy in my lab, like at the LHC, but when I go perpendicular and when I go to S equal to I epsilon. But if I go up in the imaginary direction, what do I conclude? Alpha is not only in R, it must be positive. Right? And this is this causality condition that I believe Nima spoke about. So this was something that Nima understood already several years ago, Nima and collaborators. That these first terms in the effective field theory, these quartic couplings, that they can't take any sign, they need to be positive. Okay, and here we see it's a consequence of unitarity, but in this more powerful sense, in the sense that if the function is smaller than 1 everywhere, as I move inside, it must decrease in absolute value. It can start increasing. If it starts increasing when I go perpendicular, it's because there are more singularities here in the complex plane that there cannot be. So the fact that there is not going to be any singularities upstairs is the statement that the function must decrease when I go up. Right? And what we are going to see next time, and this is what is novel and has some applications for some effective field theory, is that now you could ask, but if I take this function f with some regular expansion, from this argument I only learn about this first effective field theory term, that it needs to be positive. But what about all the terms in the effective field theory action, this beta, gamma, delta, and so on? Right? And the claim is that they would be bounded by these Schwarzspec equalities. If I plug this function and impose that it's smaller than 1, it will automatically put bounds on all the effective field theory coefficients, and that's what we are going to start seeing next time. Okay? And this would be less trivial bounds. For example, we will see a bound that some gamma here needs to be bigger than 1 over 768, for example, in some units. And that will be a consequence of these Schwarzspec lemmas. Okay? Okay, so I think we stop here today. Thank you. There was a question there?
Yeah, so history in higher dimensions of always cutting. Because E is not 0, you still have some.
Yeah, this statement is also true. The proof is a bit different. The question is whether in higher dimensions we can also say something about the sign of the first of these quartic couplings in effective field theory. Can we also argue by unitarity and causality and so on? Indeed, that was the paper of Katazi and Niemann and Dubovsky and others, was exactly showing how to do it. But it's less trivial from the point of view of amplitudes, precisely because of what you say, that in general for t not equal to 0, when the angle is not 0, the cuts don't collide exactly. The analysis they did, if I remember correctly, at the level of amplitude was at the level of partial waves, where the cuts collide again. So, but it's less. It's much more non-trivial. Yeah, that statement is less trivial there.
Any more questions? Thank Pedro again.
Instead of 1 or 3 or 4?
Yeah, yeah. You can generalize this.
What theories are?
For example, with 3 poles, we will get this E8 Ising model, for example. That's an example that I'm going to discuss next time.
The AC